Good afternoon, calculus students. So this is Mr. Chen again. So welcome back to my channel. So last time I talked about sections 9.1 with sequences in series, with the limit, all that kind of test. But this one is a continuation. So of 9.1b, so limit of sequences. So the sequence theorem, so if limit of a sub n as n approaches infinity, so that equals L, and then limit of b sub n as n goes to infinity, so that equals L. And there exists an integer capital N such that a sub n it's less than c sub n, it's less than b sub n. For all little n, it's greater than capital N. Then that means the limit of c sub n goes to infinity, so that equals L. So we talked about that previously for the squeeze theorem of the functions. So if the function is being bounded with the limit from both sides, the left and the right, or the upper limit, the lower limit, so therefore the limit for c sub n, or for the function in between, it's always considered the same limit. So basically we can apply that for sequences in series as well. And then for the absolute value theorem, if limit of absolute value of a sub n as n approaches infinity equals 0, then the limit of a sub n as n approaches infinity, so that also equals 0. So here's the example. So using that, the squeeze theorem. So this one, anytime they see like -1 to the power of n, so normally this one is considered alternating sequence. So we'll get to that in the later sections of this chapter. So let's say that n is considered an odd integer. Okay, so odd integers such as 1, 3, 5, so on and so forth. So we plug in that odd integer, we do have -1 to the power of any odd integer. And then the denominator, so odd integer plus 1. So for the limit like this, so let's say that n it's like 1001. So if that's -1 to 1001, so we do know that this one is always considered -1 because that's the odd power. Denominator, this one is going to be 1002, so it's going to be a big number. So a constant over a very big number, so that it's going to be 0. So now what happens if I plug in n, it's an even integer. So let's say that if I plug in 1002, so -1 to the power of even integer, so this one is going to be considered positive 1. And then the denominator, it's going to be even number plus 1. So 1002 plus 1 is going to be 1003. So it's going to be a big number. So again, if that's a constant over a big number, so that means eventually it's going to be 0. So by using the squeeze theorem, if the limit of a sub n as n approaches infinity equals L, and then the limit of b sub n approaches infinity equals L, so that means the limit of c sub n as n approaches infinity, it's also L. So therefore, the limit for this one, the sequence of -1 to the power of n over n plus 1, so that equals 0. And then method number 2, we're using the absolute value theorem. So take the limit as n approaches infinity, absolute value of -1 to the power of n all over n plus 1. So as you can see that it doesn't matter what kind of n value that you have. So absolute value, it guaranteed that it's going to be a constant, whether that's plus minus 1 all over infinity with the absolute value. So therefore this one is going to be considered 0. So again, using that, the conditional statement, the absolute value theorem, if the limit of absolute value of a sub n as n approaches infinity equals 0, then the limit of a sub n goes to infinity, also goes to 0. So therefore, so the limit n goes to infinity, a sub n, so that equals 0. So making sure that you guys understand the concept, the new theorem, the squeeze theorem, things that we talked about for the limit previously. That was a long time ago, back to calculus AB. And then the other one, the absolute value theorem. So it doesn't matter whether that's negative or positive. Once you take absolute value, it guarantees that it's always positive or 0. So once we've been able to find out the limit like that, so therefore the limit for the sequence, it's 0. Okay, so now for the example, the practice, so this one pretty much doing the same thing. So limit as n approaches infinity. If you plug infinity, so we got infinity over the quantity of infinity plus 1, which is considered indeterminate form. It's like infinity over infinity. So basically we can apply the L'Hopital's rule. So pretend that n is just like the function x, the independent variable. So we just take the derivative. So derivative of n is just 1. Derivative of n plus 1, it's also 1. So 1 over 1, which is 1. So therefore the limit as n approaches infinity of the sequence, n over n plus 1, so that equals 1. And then get a one similar situation, so limit as n approaches infinity of natural log of n over n. So natural log of infinity over infinity. So we got infinity over infinity, which is another, well, it's just the same kind of indeterminate form. So using the L'Hopital's rule, so take the derivative of natural log of n, we got 1 over n. Denominator and derivative of that is just 1. So 1 over infinity. So that just considered 1. And now what about the one that's a little bit more complicated? So let's say that we do have a sequence of the set of a sub n equals n factorial over n to the power of n. So discuss convergence or divergence. So look at the few terms right here. So we do have, well, let's say n equals 1 first. So we do have 1 factorial over 1 to the power of 1. So basically that is just considered 1. But what about if n equals 2? So we do have 2 factorial. So just plug in the number 2 factorial over 2 to the power 2. So 2 to the power of 2, that's 4. And then 2 factorial, that's like 2 times 1, which is 2. So it's 1 half. As you can see that the number is getting smaller if n is getting bigger. So n equals 3, so we do have 3 factorial over 3 to the power of 3. So 3 to the power of 3, so that's 27. And then 3 factorial, we do have 3 times 2 times 1, which is what, 6. So the number is getting smaller and smaller. So the term seems to be decreasing. So it's getting smaller and smaller. And the last term of the sequence of a sub n, most likely, it's going to be 0. And we can rewrite this as the limit n goes to infinity of 1 over n. Well, the reason why that is because it doesn't matter what kind of number we have on the top. It's always a constant. It's just a small constant. It might be getting bigger for the numerator, but the denominator, the rate to change that, it's even faster. So if we just convert that to the derivative, we can see that the derivative of this functions, it's going to be positive. It's going to be negative. So that means the original function is going to be considered decreasing. So we can conclude that the limit of 1 over n as n approaches infinity, so that equals 0. So therefore, by the absolute value theorem for the limit test, so we can conclude that limit as a sub n, as n approaches infinity, a sub n, so that equals 0. So important things to note. So it can be shown that limit k of k to the power of n over n factorial as n approaches infinity equals 0 for any value of k. So k is just the arbitrary constant. And then n factorial always, so this kind of expression always grows faster than any exponential functions. Okay, so exponential functions such as what? It's like a constant to the power of n, so it's always growing faster. If you see anything like this, so n factorial, it's always greater than a to the power of n. So do you remember what a monotonic function is? So monotonic function, so that means it's either strictly increasing or strictly decreasing. So let's say we have exponential function going like that, strictly increasing, or the other one, exponential decay, strictly decreasing. So a monotonic sequence, so pretty similar situations. So it's a sequence whose term is either increasing or increase. Okay, so let's just use those kind of action word. Increase or decrease. So determine whether or not a sequence is monotonic. Okay, so just by plugging few number right here for n, so let's say that n equals 1, so we do have 3 over 1 plus 1, so we do have 3 over 2. And then when n equals 2, so we do have 3 over 2 plus 1, which is 3 over 3. So that's 1. As you can see that the number is getting smaller. And then n equals 3, so we got 3 over 3 plus 1, so it's 3 over 4. So this one, it's always decreasing because that, well, another thing you can say that it's the limit as n approaches infinity, 3 over n plus 1. So that equals 3 over infinity, which is 0. If the relationship is not so obvious, a little work may be required to show that a sub n equals n over n squared plus 1. It's always decreasing. So first thing that I want to show is that n equals 1, n equals 2. So once you finish that, the arbitrary case, okay, so this one you want to put it in general. So n equals 1, so we do have 1 over 1 squared plus 1, which is 1 over 2. And then 1 over, well, when n equals 2, so we do have 2 squared plus 1, so that's going to be 1/5. But this one is just for like the specific example. So in terms of doing it in the general cases, so we need to start it off with a sub n plus 1. So this one basically shows that the number, the sequence is getting smaller, it's decreasing. So let's find out a sub n plus 1. So we do have n plus 1 over n plus 1 quantity squared plus 1. And then we want to compare that. So a sub n, it's less than a sub n plus 1. So a sub n, that's just the original sequence term. So we do have n over n squared plus 1. So this one is less than n plus 1 over n plus 1 quantity squared plus 1. So in order to do that, so we need to show that n is going to be less than or greater than any kind of arbitrary number. So I'm going to pull this out to the new slide here so I can use more space to show work, okay? So let me go back to my home page. So anytime that you deal with things like this kind of complicated situation, we'll not just do it with the specific value of n, but also we need to do it in the general form. So the one that we need to find out is that a sub n plus 1. Okay, let me open up the new slide for this one. Oops. So let's see what we got right here. And going back to the example. Oops, right here. It's a lot of browser that I open up here, so let's see. So for this one, we do have n over n squared plus 1. It's less than n plus 1 over n plus 1 quantity squared plus 1. Okay, let's put it right here. If you guys do recognize the way to solve for the nonlinear system or the nonlinear inequality. Okay, so first thing that you can do, you can always cross multiply. We don't want to deal with those denominator. So basically we got n times n plus 1 quantity squared plus 1. Okay, for this whole quantity. And then it's less than n plus 1 times n squared plus 1. So now what we can do next, so this one we can obviously distribute. Okay, so distribute and then try to find out things that we can cancel on both sides. So we got n plus 1 quantity squared, so it's n squared plus 2n plus 1. So 1 plus 1, then that'll be plus 2. And then on the right hand side, so this one basically we just want to FOIL, so n cubed plus n squared plus 1. And then also the left hand side, distribute, so this one n cubed plus 2n squared plus 2n. So for those you might be wondering things that we can cancel on both sides, we can cancel out that n cubed, we can cancel out that n squared. Well, subtract that n squared on both sides, we do have 2n squared minus n squared, then that'll be n squared. Combine those like terms, 2n minus n, so we do have 1n whatever that constant you have on the right hand side, you want to bring it back to the left hand side, so subtract 1, so it's less than 0. So obviously this one is non-factorable, so that's non-factorable. Another thing that we can do, so basically you can just using that the quadratic formula. So A, which is 1, B, it's 1, so C is negative 1, so quadratic formula, so N equals negative B, negative 1 plus minus, so 1 squared minus 4AC, so 4 times 1 times negative 1, all over 2 times 1. So we do have negative 1 plus minus, so 1 plus 4, which is 5, all over 2. So this one, well, N gonna be a perfect number, so it looks like this one is not gonna be a perfect number. But the thing is that N, it's always a positive integer because that's a sequence is in series. So that means it's negative 1 plus root 5 over 2. So anytime that when N it's greater than negative 1 plus root 5 over 2, so this statement, it's always true. Okay? So now going back to what we found. So the one I just showed you right there, the continuation, so showing that a sub n, it's always considered less than a sub n plus 1. So once you solve for n. So another useful method for showing that the sequence is monotonic is to use the derivative of the related functions. So we cannot use the derivative of the sequence because a sequence, it's not a function. Okay, so the thing is, so choose a function that is always negative or positive. So using the first derivative test, whose y value match the term of the sequences at each whole number as x equals n. Okay. So let's say that if the derivative of the function is always positive, then the related sequence is always increasing. If the derivative of the function is negative, then the related sequence is always decreasing. So basically this one is just using that the first derivative test. So we care about whether or not a sequence is increasing. It's being bounded. It's bounded. Okay, this one just say that, bounded. I'll explain that what that means here. Because of the theorem below, every bounded monotonic sequence is converging. Okay, so bounded means that the sequence has a limit beyond which it does not go. Okay, so let's say that we do have a decreasing sequence. As you can see that this one is getting close to 0 for this horizontal asymptote here, the x-axis. So this one is considered a decreasing sequence. So if that shows like either increasing or decreasing, so that means the sequence is considered monotonic. Okay, so a sequence it's let's say this one is considered increasing. If there's a number m such that a sub n it's less than or equal to capital M. For any value n is greater than or equal to 1. So again, n is just the number of terms. 1, 2, 3, 4, 5. So m is called the so this one I would say that it's called the upper bound. So let's say that if this one is increasing, so going this way, so here's m. So this one is called the upper bound. And then a sequence is decreasing. And there's a number L such that a sub n it's greater than or equal to L. For all n is greater than or equal to 1. So L is called the lower bound. So let's say that this one is decreasing. So here's L. So L is called the lower bound. So a sequence is bounded. Okay, well, let's see. If it's bounded both above or below. Oh, sequence is monotonic. Or can say that the sequence is converging if it's being bounded above or below. Okay, so the sequence is converging. If it's bounded both above or below. Okay, so what that means is anytime they see things like this, kind of like a sideways cubic curve, but this one is like bunch of dots. So bounded in between. So bounded both above or below, like that. So this one is always considered a monotonic sequence, and also it's convergent. So sketch the drawing your teacher shown below. So I just did it right here. So if that's increasing, so n, which is greater than or equal to a sub n, and for any value of n is greater than or equal to 1, so this one is called the upper bound. And then L down here, so it's called the lower bound. And the sequence is always convergent if the sequence is considered monotonic and it's being bounded above or below. So again, let me just redraw the third one. So let's say that we do have M up here and then L down here, and the sequence is going this way, increasing. So bounded in between, above and below. Okay, so make sure that you guys understand the concept, things that we're talking about today. So the sequence, the Squeeze Theorem, and the absolute value, and also the monotonic sequence. Okay, and also the sequence, we can use the similar function to represent, and then to find the derivative, to find out whether that is considered increasing or decreasing. So we can determine the sequence is either monotonic or non-monotonic. Okay, so thank you for watching the video today. So I'll see you guys next time. Take care.